Thank you so much for coming to our session this morning. I'm Sirajuddin. I'm on the TensorFlow Lite team. And we work on bringing machine learning to mobile and small devices. And later on, I will introduce my colleague, Andrew Selle, who will be doing the second half of this talk. So the last couple of days have been really fun for me. I've gotten to meet and speak with many of you. And it's been really nice to see the excitement around TensorFlow Lite. And today, I'm happy to be here and talk to you about all the work that our team is doing to make machine learning on small devices possible and easy. So in today's talk, we'll cover 3 areas. First, we'll talk about why machine learning directly on device is important and how it's different than what you may do on the server. Second, we'll walk you through what we have built with TensorFlow Lite. And lastly, we'll show you how you can use TensorFlow Lite in your own apps. So first, let's talk about devices for a bit. What do we mean when we say a device? Well, usually a mobile device, basically our phones. So our phones are with us all the time. We interact with them so many times during the day. And modern phones come with a large number of sensors on them, which give us really rich data about the physical world around us. Another category of devices is what we call edge devices. And this industry has seen a huge explosion in the last few years. So some examples are smart speakers, smart watches, smart cameras. And as this market has grown, we see that technology which only used to be available on more expensive devices is now available on far cheaper ones. So now we are seeing that there is this massive growth in devices. They're becoming increasingly capable, both mobile and edge. And this is opening up many opportunities for novel applications for machine learning. So I expect that many of you are already familiar with the basic idea of machine learning. But for those that aren't, I'm going to really quickly cover the core concept. So let's start with an example of something that we may want to do. Let's say classification of images. So how do we do this? So in the past, what we would have done was to write a lot of rules that were hard-coded, very specific, about some specific characteristics that we expected to see in parts of the image. This was time-consuming, hard to do, and frankly didn't work all that well. And this is where machine learning comes in. With machine learning, we learn based on examples. So a simple way to think about machine learning is that we use algorithms to learn from data, and then we make predictions about similar data that has not been seen before. So it's a 2-step process. First, the model learns, and then we use it to make predictions. The process of model learning is what we typically call training, and when the model is making predictions about data is what we call inference. This is a high-level view of what's happening during training. The model is passed in labeled data, that is input data, along with the associated prediction. And since in this case, we know what the right answer is, we are able to calculate the error. That is, how many times is the model getting it wrong, and by how much. We use these errors to improve the model. And this process is repeated many, many times until we reach the point that we think that the model is good enough, or that this is the best that we can do. This involves a lot of steps and coordination, and that is why we need a framework to make this easier. And this is where TensorFlow comes in. It's Google's framework for machine learning. It makes it easy to train and build neural networks. And it is cross-platform. It works on CPUs, GPUs, TPUs, as well as mobile and embedded platforms. And the mobile and embedded piece of TensorFlow, which we call TensorFlow Lite, is what we are going to be focusing on in our talk today. So now I want to talk about why would you consider doing machine learning directly on device. And there are several reasons that you may consider. But probably the most important one is latency. If the processing is happening on the device, then you're not sending data back and forth to the server. So if your use case involves real-time processing of data such as audio or video, then it's quite likely that you would consider doing this. Other reasons are that your processing can happen even when your device is not connected to the internet. The data stays on device. This is really useful if you're working with sensitive user data, which you don't want to put on servers. It's more power efficient because your device is not spending power transmitting data back and forth. And lastly, we are in a position to take advantage of all the sensor data that's already available and accessible on the device. So this is all great, but there's a catch, like there always is. And the catch is that doing on-device ML is hard. Many of these devices have some pretty tight constraints. They have small batteries, tight memory, and very little computation power. TensorFlow was built for processing on the server, and it wasn't a great fit for these use cases. And that is the reason that we built TensorFlow Lite. It's a lightweight machine learning library for mobile and embedded platforms. So this is a high-level overview of the system. It consists of a converter where we convert models from TensorFlow format to TensorFlow Lite format. And for efficiency reasons, we use a format which is different. Then it consists of an interpreter which runs on device. There are a library of ops and kernels. And then we have APIs which allow us to take advantage of hardware acceleration whenever it is available. TensorFlow Lite is cross-platform, so it works on Android, iOS, Linux. And a high-level developer workflow here would be to take a trained TensorFlow model, convert it to TensorFlow Lite format, and then update your apps to use the TensorFlow Lite interpreter using the appropriate API. On iOS, developers also have the option of using CoreML instead. And what they would do here is to take their trained TensorFlow model and convert it to CoreML using the TensorFlow to CoreML converter, and then use the converted model with the CoreML runtime. So the two common questions that we get when we talk to developers about TensorFlow Lite is it small and is it fast? So let's talk about the first question. One of our fundamental design goals with TensorFlow Lite was to keep the memory and binary size small. And I'm happy to say that the size of our core interpreter is only 75 kilobytes. And when you include all the supported ops, this size is 400 kilobytes. So how did we do this? So first of all, we've been really careful about which dependencies we include. Secondly, TensorFlow Lite uses flat buffers, which are far more memory efficient than protocol buffers are. One other feature that I want to call out here in TensorFlow Lite is what we call selective registration. And that allows developers to only use the ops that their model needs, and thus they can keep the footprint small. Now moving on to the second question, which is of speed. So we made several design choices throughout the system to enable fast startup, low latency, and high throughput. So let's start with the model file format. TensorFlow Lite uses flat buffers, like I said. And flat buffers is a cross-platform efficient serialization library. It was originally created at Google for game development and is now being used for other performance-sensitive applications. The advantage of using flat buffers is that we can directly access the data without doing parsing or unparsing of the large files which contain weights. Another thing that we do at the time of conversion is that we prefuse the activations and biases. And this leads to faster execution later at runtime. The TensorFlow Lite interpreter uses a static memory and static execution plan. This leads to faster load times. Many of the kernels that TensorFlow Lite comes with have been specially optimized to run fast on ARM CPUs. Now let's talk about hardware acceleration. As machine learning has grown in prominence, it has spurred quite a bit of innovation at the silicon layer as well. And many hardware companies are investing in building custom chips which can accelerate neural network processing. GPUs and DSPs, which have been around for some time, are also now being increasingly used to do machine learning tasks. TensorFlow Lite was designed to take advantage of hardware acceleration, whether it is through GPUs, DSPs, or custom AI chips. On Android, the recently released Android Neural Network API is an abstraction layer, which makes it easy for TensorFlow Lite to take advantage of the underlying acceleration. And the way this works is that hardware vendors write specialized drivers or custom acceleration code for their hardware platforms and integrate with the Android NN API. TensorFlow Lite, in turn, integrates with the Android NN API via its internal delegation API. A point to note here is that developers only need to integrate their apps with TensorFlow Lite. TensorFlow Lite will take care of abstracting away the details of hardware acceleration from them. In addition to the Android NN API, we are also working on building direct GPU acceleration in TensorFlow Lite. GPUs are widely available and used. And like I said before, they are now being increasingly used for doing machine learning tasks. Similar to NN API, developers only integrate with TensorFlow Lite if they want to take advantage of the GPU acceleration. So the last bit on performance that I want to talk about is quantization. And this is a good example of an optimization which cuts across several components in our system. So first of all, what is quantization? A simple way to think about it is that it refers to techniques to store numbers and to perform calculations on numbers in formats that are more compact than 32-bit floating point representations. And why is this important? Well, for two reasons. First, model size is a concern for small devices. So the smaller the model, the better it is. Secondly, there are many processors which have specialized SIMD instruction sets which process fixed point numbers much faster than they process floating point numbers. So the next question here is, how much accuracy do we lose if we are using 8 bits or 16 bits instead of the 32 bits which are used for representing floating point numbers? Well, the answer obviously depends on which model that we are using. But in general, the learning process is robust to noise. And quantization can be thought of as a form of noise. So what we find is that the accuracies tend to be usually within acceptable thresholds. A simple way of doing quantization is to shrink the weights and biases after training. And we are shortly going to be releasing a tool which developers can use to shrink the size of their models. In addition to that, we have been actively working on doing quantization at training time. And this is an active area of ongoing research. And what we find here is that we are able to get accuracies which are comparable to the floating point models for architectures like MobileNet as well as Inception. And we recently released a tool which allows developers to use this. And we are working on adding support for more models in this. OK, so I talked about a bunch of performance optimizations. Now let's talk about what does it translate to in terms of numbers. So we benchmarked 2 models, MobileNet and Inception v3, on the Pixel 2. And as you can see here, we are getting speedups of more than 3 times. When we compare quantized models running on TensorFlow Lite versus floating point models running on TensorFlow. I'll point out here that these numbers do not include any hardware acceleration. We've done some initial benchmarking with hardware acceleration, and we see additional speedups of 3 to 4 times with that, which is really promising and exciting. So stay tuned in the next few months to hear more on that. Now that I've talked about the design of TensorFlow and performance, I want to show you what TensorFlow Lite can do in practice. Let's please roll the video. Oh, so this is a simple demo application which is running the MobileNet classification model, which we trained on common office objects. And as you can see, it's doing a good job detecting them, even this TensorFlow logo that we trained this model on. Like I said, it's cross-platform, so it's running on iOS as well as Android, and we also are running it here on Android Things. This was a simple demo. We have more exciting demos for you later on in the talk. Now let's talk about production use cases. I'm happy to say that we've been working with partner teams inside Google to bring TensorFlow Lite to Google Apps. So portrait mode on Android camera, Hey Google and Google Assistant, and Smart Reply are some features which are going to be powered by TensorFlow Lite in the next few months. Additionally, TensorFlow Lite is the machine learning engine which is powering the custom model functionality in the newly announced MLKit. And for those of you that may have missed the announcement, MLKit is a machine learning SDK. It exposes both on-device and cloud-powered APIs for machine learning, as well as the ability to bring your own custom models and use them. These are some examples of apps that are already using TensorFlow Lite via MLKit. PixArt, it's a really popular photo editing and collage making app. And Visco, it's a really cool photography app. So back to TensorFlow Lite and what is currently supported. So we have support for 50 commonly used operations, which developers can use in their own models. I will point out here that if you need an op which is not currently supported, you do have the option of using what we call a custom op and using that. And later on in this talk, Andrew will show you how you can do that. Op support is currently limited to inference. We will be working on adding training support in the future. We support several common popular open source models, as well as the quantized counterparts for some of them. And with this, I'm going to invite my colleague, Andrew, to talk to you about how you can use TensorFlow Lite in your own apps.
Thanks, Sarah. So now that you know what TensorFlow Lite is and what it can do and where it can be run, I'm sure you want to know how to use it. So we can break that up into 4 important steps. The first one, and probably the most important, is get a model. You need to decide what you want to do. It could be image classification, it could be object detection, or it could be even speech recognition. Whatever that model is, you need to train it yourself. You can do that with TensorFlow, just like you trained any other TensorFlow model. Or you can download a pre-trained model if you're not ready to make your own model yet, or if an existing model satisfies your needs. Second, you need to convert your model from TensorFlow to TensorFlow Lite, and we'll show some examples of how to do that in a second. Third, if there's any custom ops that you need to write, this could be because you want to spot optimize something with some special instructions you know about, or it could be that you're using a piece of functionality that we do not yet support, like a specialized piece of signal processing. Whatever it might be, you can write your ops. This may not be necessary, of course. The last step is to write an app, and you're going to use whatever client API is appropriate for the target platform. So let's dive into some code. Converting your TensorFlow model. Once you're done with a TensorFlow training, you typically have a saved model, or you might have a graph-def. What you need to do first is put this through the converter. So here I'm showing how to do this within Python. So if you download the normal TensorFlow tooling that's precompiled, like the pip, you're able to run the converter. And it just takes a save model directory in or a frozen graph-def, and you specify a file name of what TFLite file you want. And that will output a flat buffer that's on disk that you can now ship to whatever device you want. Now, how might you get it to the device? You could put it into the package. You could also, say, distribute it through a cloud service where you can update your model on the fly without updating your core application. Whatever you want to do is possible. So next, once you've converted, well, you might actually run into some issues doing the conversion because there's a couple of things that can go wrong. So the first one is you need to make sure that you have a frozen graph-def or a save model. Both of these are able to get rid of the parts of the graph that are used for training. These are typically things like variable assignment, variable initialization, optimization passes. These are not strictly necessary for doing inference, that is prediction. So you want to get rid of those out of the graph because we don't want to support those operations right now because we want to have the smallest version of the runtime that can be distributed to keep your binary size small. The second thing that you need to do is make sure that you write any custom operators that you need. And now I'll go into a little bit of an example of doing that. Well, before that, let me tell you one more thing, which is we also have some visualizers that let you understand the model that you've transformed and the transformation process. So take a look at those. They're linked off of the documentation. So let's get into writing a custom op. So what kind of op might we need? Well, here I have an example that's a little bit silly, but it's to return pi. So the important thing when you write an op is that you need to implement 4 C functions. So we have a C API for defining operations. And the reason we do this is that all of our operations are implemented in this way so they can run on devices that only support C eventually. But you can write kernels in C++. In this case, what I'm doing is I'm ignoring the input tensors and I'm putting an output tensor, which is mpi. Now, if you had input tensors and you wanted to make an output tensor, you could also read the input tensors and then say, oh, multiply by 3, and now I have a multiply by 3 operation. This is going to be application dependent. And of course, as I said before, you don't always need to do this. I'm just laying this out here to show that if there's some functionality that you need, we are extensible. OK. Once you've converted your model, you need to use a client API. Let me start with the C++ API, but we have other language bindings as well that I'll get to. But in any of the bindings, it's going to follow the same basic pattern. The pattern is create an interpreter and load the model, fill in your data, execute the model, and read back your data. So it's very simple. So in the C++ API, the first thing you do is create a model object. And this is given the file name of the TensorFlow Lite file, and it creates an object that is going to hold that model and mmap it. So as I said before, we use flat buffers, and the reason why is that we can mmap the buffers, which means that there is 0 latency to start running the model effectively. OK, second, if you have any custom operations, you can register them. So basically, at this phase, you're deciding which operations to include into your runtime. By default, we provide a built-in op resolver that includes all of our default operations. You might also use selective registration that we alluded to before, where you include only a subset of the operations. In this case, you might provide a minimal resolver. And if you wanted to use the custom operation that we had before, you would create a custom resolver that would tell TensorFlow Lite how to find your custom operation. So now we know what our ops are and where to get the code for them, and we know our model. Now we need to create an interpreter object. So we take the pair of model and resolver and put it together, and it returns an interpreter. This interpreter is going to be our handle for doing our execution. So the next step is we're going to perform our execution. But before we can do that, we need to fill the buffer. So if you have a model like a classification model, that is something that takes an image in. Where are you going to get that image? Well, the obvious place you might get it would be from your device's storage, if it's an image file name, but also commonly would be a camera. Whatever it might be, you produce a buffer. In this case, it's going to be a float star and an instar buffer, and you fill it into our buffer. And once you fill this buffer, you're ready to run. So we filled our buffer. TensorFlow Lite has all the information it needs to run the execution, and we just call invoke. Now it's going to block until that execution is done, and then we're going to be able to read the output of it in an analogous way to our input. So that is, we can get a float star buffer out, which could represent the class numbers. And then you're free to do with that data whatever you want. So for example, in an image classification app that we showed before, you would read that index out, map it back to a string, and then put it into your GUI's display. Great. So now we know how to use C++. What if you're using another platform? For example, Raspberry Pi. On Raspberry Pi, the most common thing to use is probably Python. And again, it's going to follow the same basic pattern. First, we create an interpreter object. The interpreter object is now our handle. How do we feed data? Well, since it's Python, we can use NumPy arrays. And this is really convenient, because if you need to do pre-processing or post-processing, you can do it with the primitives that you're familiar with. And this is kind of a theme that goes on, that we want to keep our bindings as idiomatic as possible in the language that they are, and also keep it performant. So in this case, we put in some NumPy array, and we take out some NumPy array. So that's Python. What if you're writing an Android app, or you want to write an Android Things application? Then you might use the Java API. So in this case, it's the same thing. You build an interpreter, give it the file name of the interpreter. It might be from a resource if you're doing an Android application. And then finally, you're going to fill the inputs in and call run. So one of the things that we did for the Java API is that we know that many Java programmers don't really want to deal with building their own native library. So in that case, you can just use our Gradle file here, which will include our pre-compiled version of TensorFlow Lite. You don't have to download our source code. And even for the tooling parts where you do the conversion from TensorFlow to TensorFlow Lite, you can download the pre-compiled version of TensorFlow, as I alluded to before. Great. So what if you're doing iOS? Well, in that case, you can use the C++ API. You can also use the Objective-C API. But again, we provide a pre-compiled binary in the form of a CocoaPod. OK. So now that you know how to use TensorFlow Lite, I want to tell you a little bit about what's going to be coming up in TensorFlow Lite. One thing that we've been asked for a lot is adding more operations. So the more operations that we add, the more models can be run from TensorFlow out of the box. The other thing that happens with machine learning that's often difficult is that researchers come up with new techniques all the time. And that means that TensorFlow is always adding operations. That means that we're going to continue to follow TensorFlow as it adds important operations and add them into TensorFlow Lite as well. OK. The second thing we're going to do is we're going to improve the tooling, provide better documentation and tutorials, and try to focus on ease of use. So it's really easy for you to understand on end-to-end examples how to integrate TensorFlow Lite. And the third thing, which Sarah already mentioned, but I'll mention again, is that we're excited about on-device training. On-device training is really exciting because it allows us to refine a model based on a user's experience. It allows us to decouple that experience from going to the cloud. So if they're disconnected, we can continue improving the model. So there's a lot of requests for this. This, of course, will require more and more computation on the device, but we're excited about upcoming hardware accelerators that will make this more and more possible. OK. One more question before we get into some exciting demos. When should I use TensorFlow Lite? So as we alluded to before, we're starting to use TensorFlow Lite for our first-party applications, and third-party applications are also using it. That means that what we're doing moving forward is that we're going to make TensorFlow Lite our standard solution for running ML on small devices and mobile devices. TensorFlow Lite currently supports a subset of TensorFlow ops. This means that our recommendation is that you should use TensorFlow Lite if you can, and let us know. And let us know about any missing functionality you need. It's not quite done. You probably want to see our demos. So with that, I want to show you a video of retrained models. We showed you that TensorFlow logo being recognized. This is a common theme that we get, which is people like our pre-trained examples, like MobileNet, but they may not have an application where they need to tell the difference between 5 dog breeds and many zoo animals. They might have an office scenario where they have markers and whiteboards. And in fact, as we were testing the app, we found we had this issue too. It's like we don't have the classes that are in these pre-trained models. So one of the great things that one of our other TensorFlow members created was something called TensorFlow for Poets. And there was a code lab about that, and it's available online as well. And it basically allows you to take a pre-trained image model that has really good detector ability and put your own classes into it. And I want to show you a demo app that we created that runs on the PC and creates TensorFlow Lite models for you. So can we go to the video? OK, so we showed you before. Can we recognize scissors and Post-it notes? Well, let's try it out. You always want to try these models, check. OK, the scissors looks good, right? OK, great. Post-it notes also looks good. But what if we had another object, an object that's more common, more important, like this metal TensorFlow logo? This happens in everyday life, right? OK. Let's go take a look at how this does. Well, it's labeled as other. That's not very good. But the great thing about machine learning is that we can fix this. And the way we fix it is we add data. So we have our application. We've gone to our training tab now. And now we're going to define a class called TensorFlow. And this is basically short for TensorFlow logo. And now from our webcam, we're going to click Capture, and we're going to capture a couple of different perspectives, as many as we can. And ideally, you would take it on different backgrounds, so it doesn't associate the background with it being a TensorFlow logo. Then I click the Train button, and right now it's using TensorFlow to train the model, and you can see it's converging to a good validation accuracy. It's going to reload the model, and we're testing it in TensorFlow Lite, running on the PC right now, and we see that it's recognizing TensorFlow correctly. So it's that fast and easy. But also, we can take that model and we can move to Android and iOS and use the exact same model and update it. So thanks. Now let's move to a live demo. So I'm going to go over here to the podium. All right. OK, so classification, what I just showed you is kind of this idea that you have an image in, and you put an image out, and you put classifications out. But what if you have multiple objects in the scene, or you have something in a corner of an object? You also want to know where in the scene that object is. And that enters this model called single-shot detection. It's a type of model. And it turns out that our friends in TensorFlow Research released a package called object detection as part of the TensorFlow models. And that basically allows you to use their pre-trained model that recognizes many classes. So what I've done is I want to load that onto a small device. In this case, we've shown you a lot of things about mobile devices. I want to show you another small device. This is a Raspberry Pi. So the Raspberry Pi is a really cool example of a device because it's very cheap and easy to get. So any high school student can have one of these. You can have many of these and just use them for a dedicated project. But the other great thing about them is not only are they relatively powerful, but they're also able to interface with other hardware. They have GPIO pins. This can be capitalized in a number of different ways, but one way is to run Linux, and that's what we're doing here. But you can also use Android Things, which you can see one of the cool the sandbox has many examples of doing that. So you could also do this with Android Things. So in this case, I have the system board right here, and it's connected to a motor controller. And this motor controller is just a microcontroller that interfaces to servo motors. These servo motors can go up and down, left and right, and they can basically aim the camera. So now what we're going to do is we're going to load our object detection model onto this device, and we're going to actually run it in order to recognize different objects. So let's go to the demo feed, please. And we can see my app. You can tell by the beautiful nature of this app that I'm not a great app developer, but this is what I can do on a weekend, so give me a little bit of slack. OK, so here if we hold up the apple, it's recognizing the apple, and it's telling us what probability and where the object is. Now, that's all good and fine, but when we couple it with the ability to move, where I'm going to turn on the motors now, and now I'm going to bring back the apple, and what I'm going to do is I'm going to move the apple in the screen, and it's going to try to keep it centered. So as I move this apple, it's basically going to try to keep it centered. So it's like a little virtual camera person. And this works on other objects, like this banana here, hopefully. Oh, there we go. And it's going to keep that centered. And if you put two objects in the screen, it's going to try to keep them both in. OK, so we get a little bit of false detections. But basically, it's going to try to keep them both centered. So this is really a fun application, and I bet you can come up with many different applications that are really exciting to do with this type of application. So can we go back to the slides again? And I'll get my clicker. So like I said, this is basically what I can do in a weekend, but I imagine great app developers and people with a lot of creativity about connecting devices and connecting software can do many interesting things. So what I want to do now is I want to tell you, in summary, TensorFlow Lite, you've seen a lot about it. Basically, we feel TensorFlow Lite makes on-device ML small, fast, and easy. And we think that you're going to find it very useful in all of your applications. And we're excited to see what you build. Come talk to us. I'm going to be in office hours at 12:30. You can come talk to me. In addition, you can come to our sandbox if you haven't already. And we have, of course, the examples that I showed you here. We have the tracking camera. We also have the object classification on mobile device. But another cool thing that we have is the donkey cars. And this was done by a group outside of Google. And we converted them over to TensorFlow Lite. And we are excited to say that their application works really well with TensorFlow Lite as well. So with that, I hope you check these things out. I want to tell you that if you want to get started, you can go to our documentation page. You can go to the tensorflow.org page, and there is a TF Lite page where you can find more information about it. In addition, our code is all open source. You can get it on GitHub. You can download it, modify it, submit a pull request, and of course, file any issues that you have while using it. In addition, if you want to talk about TensorFlow Lite, talk about your applications, ask us about feature requests, please send to our mailing list. This community is really exciting. We found that in open sourcing TensorFlow, we got a lot of excitement, we got a lot of interest, and we made it a much better piece of software to use for everyone, both people inside Google and outside Google. And we hope that you'll engage TensorFlow Lite in the same way that TensorFlow has been engaged. So with that, I want to thank you for your attention, for coming to I/O, for listening to our talk about TensorFlow Lite. I also want to thank our Google partners. This product didn't come out of isolation. It came from all of our experience building mobile apps with machine intelligence. As we gained experience, we found that there was a common need, and that was the genesis of TensorFlow Lite. So all of our partners provided application, provided feedback, even provided code, and help with our models. So thank you so much to you and to them, and enjoy the rest of I/O.